Okay, so if we remember our definition of density, chat, let's start the lesson. Let's begin our lesson today, lab rats. So my goal today is fluid mechanics. We're going to do a bit of density, a bit of barometers, a bit of pressure underwater, a bit of air pressure. Hopefully explain how straws, like if I hold my coffee down, that a lot of the coffee has remained. I let go, I spilled coffee. Explain how that works. And of course, finally get to Pascal's principle. That's the goal for today's stream. Not air resistance, no. So it's a really cool thing. Or sorry, Azir, are you asking? Are you asking because are we going to ignore air resistance today? We're not going to take air resistance into consideration because air pressure has kind of got to do with air. With the Anyways, we'll talk a little bit about it. Now, first things first is we need a little bit of revision of density, the concept of density. Okay, Bambi put her paw back and she's sleeping. Density is equal to mass over volume. Density is, the symbol for it is rho. Sorry, the light is shining ever so slightly on it. Mass divided by volume. So how much an object weighs, and I say the word weight, just a little bit of a premise again. Mass is in kilograms, weight is in force, it's in newtons. So in English we say a flower weighs 1 kilogram, when in reality the proper physics terminology would be its mass is 1 kilogram. If you're asking for its weight, it would be its mass, 1 kilogram, multiplied by gravity, 9.81. So it would be 9.81 newtons would be its weight. But again, I'm going to kind of be a bit fluffy about it. That's what mass means. And volume is the amount we take up in three-dimensional space. So when we say you have a super, super dense star, or super, super dense black hole, or infinite kind of concepts like that, just imagine it's the idea of squishing matter, stuff, into a tiny, 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 tiny amount of space. That is why metal is more dense than fluff. So if I had Bunny Floof, if I pulled some of her floof from her bum because she's shedding so much, if I grabbed some of her floof from her bum and I got a piece of metal right here. Can't grab metal. There you go, my ultrasonic sensor, grab metal, right? Their volumes could be the exact same, right? The amount of space they both take up. But their densities are going to be different. First of all, because their masses are different as well. But their densities are going to be different, even if they take up the same amount of space. Metal is a lot more dense. We can squish atoms, more atoms in there than we can with the fluff, because the fluff is fluffy. You could squish the fluff down. That's a possibility as well. But that's kind of the premise of density, or side distraction over. There is a terminology we use with liquids usually, not even liquids, with things. We use something called specific gravity. And what it is it is the density of the substance compared to that of water. And there's a reason why we choose water. Now, I know this from experience because I work in a lab and I make solutions all the time. And I know off the top of my heart that the specific gravity of deionized water at a certain temperature, the idea behind it is that water, pure water, not salty water, not pure clean water, just water in general, is roughly around perfectly. It's because it's about 1,000 kilograms per. That's the value of the density of water. It's about 1,000. So it's such a beautiful number. And also we love to talk about things floating or sinking in water, that we use the term specific gravity to be a ratio number when we compare it to water. So let's talk about this. If I compare the density of something to water, and I say its specific gravity is 2.6, it means that it is 2.6 times more dense than water. If it's more dense than water, it means that it will sink. If its specific gravity is less than that of water, let's say 0.6, it's less than the water, which means it will float. We do tend to use this value when we work in most labs. We love to compare it to water. The specific value, I think, is like a certain kind of water at 4 degrees Celsius, because obviously temperature affects density, mass, volume, all that kind of stuff. So we do have usually a temperature, pressure, standard pressure kind of parameters associated with. But the change is ever so slight. For us, general human beings, we don't really care about that. We'll just say it's roughly 1,000 kilograms per meters cubed. Because if we keep referring to things with that kind of density value, 3,625 kilograms per meter cubed. If I plaster that on a material that I'm selling, majority of the population wouldn't understand that. However, if I were to say, oh, it's 2.6 times more dense than water, you know that, or its specific gravity is 2.6, you know that it will quite very, very much so sink in water. While if I say it's 0.6, it'll float. And 1 is that ratio number. 1 is the cutoff point. Higher than 1 sinks in water. Lower than 1 floats in water. And you can even determine the percentage of it that floats in water. But it's kind of like a quick number, a quick value to get your brain working, to get your brain understanding. Does that make sense, chat? Are we starting on a good ground? Do we understand what specific gravity means? It's kind of, what's the word? Not delusional, that's the wrong word. It's kind of misleading, because it sounds like you're talking about specific specific gravity in a certain area, specific gravity in a weird anomaly situation. There's, a weird terminology. Only water has the same density? No. Other material could have the same density. Pigeon, absolutely. There could be something that has the exact same density. Because ultimately, it might be very, very hard to find something exactly the same, but it depends how exact you want something to be.